In this lesson, we're going to learn about two major ways of describing data, and they would be measuring the center and measuring the variation. Center, much easier than the variation in terms of the calculation standpoint, things you've done before, such as mean, median, mode, midrange. We'll get into some examples and some definitions of that. Variation is probably something that's more new to a lot of you, and we're going to need to spend a little bit more time on the calculation, and really the important part is, what does it mean? So in the first section, 3.1, we focus on the measure of center. Now, we primarily will use mean to do so. That's going to be the primary way we do it, but we're also going to use median as well. Okay. The objective here is really not to find just one value of center, but to look at multiple values of center and kind of use those to their strengths. And every way of measuring the center that we're going to talk about has its positives and its negatives. So first, the definition of the measure of center. It's not a very good one, but it is nonetheless the definition that we're going to use, and it's the measure of center is the value at the center or the middle of the data set. Well, that's not going to tell you a whole lot that you probably didn't already know. How we interpret that center and middle of the data set will really change the different ways we measure the center. Again, mean, median, mode, midrange would be the four we use. So let's start with mean. For mean, also known as the arithmetic mean, it's the measure of center found by adding all of your data values and then dividing by the total number of data values, which is what you would typically call an average. In statistics, we don't use the word average. You never hear a statistician talk about an average. It's always a mean. But it is what you would typically call an average. Add everything up, divide by the total number. If you're looking at figuring out your average grade for something, you would add all your grades together. If there's 4 of them total, you would divide by 4, and that will tell you your average, say, test grade. Some important properties about the mean. Okay. 1, the sample mean draws from the same population tend to vary less than other measures of center. So if you take a bunch of different samples from a population, a single population, and you pull out, say, 5 different samples, and in each sample you calculate the mean from each sample, again, drawn from the same population, what you'll find is that those sample means, the mean from each sample, won't vary a whole lot. When you look at the other measures of center, they tend to vary a lot more. So this is one reason why we use sample mean a lot more than we use the other measures of center. A good thing about the sample mean is it uses every single data value to calculate it. That's not going to be the case for every one of our measures of center. There is a disadvantage, though. And the disadvantage to the mean is that just one extreme value, which we call an outlier, can drastically change the value of the mean. Okay? In which case we say that the mean is not resistant. And so if we look at the definition of resistant, a statistic is resistant if the presence of an extreme value, an outlier, does not cause a change very much. But that's not the case for mean. If you have a very, very, very high or very, very low value in your data set, and you have to add all your values up and divide by the total number, that extreme value could drastically affect what the mean will be. But that's not the case with every measure of center. So this idea of your statistic being resistant, our measure of center being resistant, is if the outliers don't have an effect. For mean, they do, so it's not resistant. Okay, here are a couple of symbols that we're going to have to start getting used to. You're going to see these a lot. This symbol right here is a sigma symbol, a summation symbol. It tells you that you're going to have the sum of a bunch of values. It tells you you're going to add a bunch of things together. X, a lowercase x specifically, is the variable used to represent an individual data value. So if we're talking about a random specific data value, we would use x to do that individual data value. Then we have n, lowercase n and capital N. Lowercase n represents the number of data values in a sample, the total number of data values in a sample, and capital N represents the total number of data values in a population. We use the capital and lowercase to distinguish between the two. We're going to do a lot of comparison between samples and populations, so we're going to have to compare the symbols as well. In this case, it's very simple to just do a lowercase and capital. And usually population, when we talk about population, we talk about really large values and samples being smaller than that. So capital and lowercase seems to fit pretty well here. So our symbol we're going to use to represent the mean of a sample is this x with a bar on top of it, which we creatively call x bar. And this stands for the mean of a sample, okay? So the way we would calculate that would be to add, which is what this symbol says to do, all our individual data values together, which is what x represents, and then divide by the total number of values in our sample, which remember is what lowercase n stands for. So that notation right there is essentially the way we calculate a sample mean. Again, x bar represents a sample mean, as opposed to this symbol right here, which we pronounce as mu. And mu represents the mean of all the population value. And again, what we would do, we would add all our values, our data values together in our population, and then divide by the total number of values in our population, which is our capital N. But mu represents the mean of a population, and x bar represents the mean from a sample. So here's an example. Dataset 32, airport data speeds in Appendix B. This is just telling you in the back of the textbook. There's a whole bunch of data sets. We're looking at dataset number 32, which has to do with airport data speeds. They looked at data speeds on a bunch of smartphones. And they looked at it for 4 different carriers. So we're just going to focus on Verizon for right now. And it said that the mean for the first 5 data speeds, so they collected 5 data speeds from Verizon, and the first 5 data speeds were 38.5, 55.6, 22.4, 14.1, and 23.1. All these are measured in megabits per second. That's your standard speed you use to measure data in a smartphone. And the question would be, let's find the mean data speed. Okay? So if we were to find the mean data speed, we would have to add all our data values together and divide by the total number. So 38.5 plus 55.6, 22.4, 14.1, 23.1, added together, divided by, there's 5 of them total, divide by 5. That would give us the mean data speed. And in this case, the mean data speed, if we took this, would be 30.74. So 30.74 is our mean data speed. So out of those first 5, the average or the mean speed that someone should expect to get at that particular airport for Verizon is 30.74 megabits per second. And that's great. That tells you, okay, on average, that's what you should expect. But one thing we got to understand is that's not going to give us all the information we are going to need. And we're going to look at variation in the next section to give us some more insight into what that means. But for right now, that's how you would calculate the mean, the average data speed for Verizon based off of that sample of 5 values. Median. The median of a data set is the measure of center that's in the middle when the original data values are arranged in increasing or decreasing magnitude. So this takes the definition of center quite literally. It says find the value that falls in the middle, okay? The key is you have to arrange your data values in order. It doesn't matter whether it's increasing or decreasing, but you have to arrange them in order to find that middle value. When I find students mess up the median, it's because they didn't do that step. They didn't arrange their data values in order for least to greatest or greatest to least, okay? Now, there's a problem when it comes to median in that it depends on how many data values you have. Okay? Whether we have an even or odd, we'll have to talk about how we do that. So some important properties is, one, the median does not change by large amounts when you include extreme values. Okay? Extreme values will not largely affect the median, so we say the median is resistant. And that's one benefit to it. The one problem is that the median doesn't actually use every single data value to collect it necessarily. If you have a very, very large value, it doesn't really matter how large it is, as long as it's just the largest value, and it really won't affect the median at all. So the only thing that affects the median is how many values you have in terms of how you're going to calculate it. The symbol we tend to use for median is this X with the tilde on top of it. So we call it, again, very creatively, X tilde. Sometimes you'll see a capital M or even MED. We're not really going to use the median all so much this semester for a lot of the things we're going to do. But in future semesters, if you deal with the median, you would see those symbols. So it's all about sorting your data values from lowest to highest, but also knowing how many you have. So, two scenarios. One, you have an odd number of data values, in which case there will be an exact middle value, in which case you find the exact middle value, and that's your median. And I'll give you an example. Second scenario is you have an even number of data values. And if you have an even number of data values, there is no middle data value. So the way we'll compute the median is by finding the mean of the two middle values. And you'll have to see this in an example to really understand probably what I'm talking about. So here's an example. Again, back to the Verizon data speeds. Here we have these 5 speeds that we need to talk about. And we have to first arrange them in order. So if we arrange them in order from lowest to highest, we see this order here. Since there are an odd number of data values, there is one value right here that sits in the middle. And that right there would be my median. So, fairly simple. Again, because an odd number, there is always going to be one middle data value. So 23.1 megabits per second is my median. Notice that it's different than the mean. And sometimes that happens and sometimes it's the same. We'll discuss that a little bit more later. Another scenario is, what if we have an even number of data values? So let's include a 6th data speed into this of 24.5. So we have our first 5 we already had before. Now we have a 6th one, 24.5. You still have to put them in order. But when you put them in order, if you notice, the middle is right here. So these two data values are the two middle values now, right? There's not a single value that sits in the middle. So the way we're going to find the median in this scenario is find the mean of the two middle values. So add them together and divide by 2, and we see we get 23.8 as our mean. But notice that this data value does not really affect the mean or this data value or any of these really in particular, other than that they're put in order. But if this number right here was drastically different, we would still have the same mean. Like, let's say this data value was 100.7. The mean wouldn't change at all. Sorry, the median wouldn't change at all. The mean would definitely change because we would have to factor that into finding the mean. But the median itself would still be the same. And so that's what we talk about, whether or not an outlier, an extreme value, affects our calculation or not. Then we have mode. Okay? The mode of a data set is the value that occurs most often or with greatest frequency. So it's all about repetition here. Modes are really good when it comes to finding center with qualitative data. Okay? Qualitative data is the non-numeric data, so the categorical data. So if we have, colors of cars in the parking lot as an example I use all the time, and you found out you had 20 yellows and 50 blues and 1,000 silvers in terms of your different car colors. The one that occurred most often would be your mode, and you would use that as your center. Now, there's a couple of problems here. One is that you could have no mode. Maybe none of the data values are repeated any more than any of the rest. You could also have more than one mode. Maybe you have 2, 3, 4 modes, okay? And we'll look at some examples of this. When finding the mode, it's as simple as just counting up your data values and finding which one occurs most. If you have two data values that occur more than anything else, we call that bimodal. If we have more than two that occur more than anything else, it's multimodal. And if you have no data value that's repeated at all, then we have no mode, okay? So this is a scenario that goes on here. So let's look at this example. Now we're moving over to Sprint instead of Verizon and looking at their data speeds. And so if we collect the Sprint data speeds, we have 0.2, 0.3, 0.3, 0.3, 0.6, 0.6, and 1.2. If you notice, 0.3 occurs more than anything else. That occurs 3 times. So then 0.3 would be our mode. It occurs most often. If we changed it to say, let's say our data speeds are 0.3, 0.3, 0.6, 0.4, and 4.0 and 4.0, well, in that case, 0.3 occurs twice, 4.0 occurs twice, 0.6 only occurs once. So the ones that occur the most are these two right here, and therefore we would have two modes, 0.3 and 4.0. What if our data set, one more time, was changed to 0.3, 1.1, 2.4, 4.0, and 5.0, in which case none of them are repeated any more than the rest. They only occur once, so then we would say there's no mode. And that's going to happen sometimes. Again, mode's not one we're going to use so much. We would use that more, again, if we did qualitative instead of our quantitative data. Finally, the last one would be midrange. The midrange of a data set is the measure of center that is the value midway between the highest and lowest values. So it's splitting your extreme values into the center is what it does. Now, if you take the highest value and you take the lowest value and you basically find the mean of those, add them together, divide by 2, that's how you would find your midrange, okay? One issue with the midrange is that it's not resistant because it only uses extreme values to calculate it, and none of the other data values are used, just the extreme values, and it finds out what's the middle point of the two extremes. So it says, okay, here's the smallest value, here's the biggest value, let's figure out what sits right in between those. And it doesn't matter if all your data values are clumped up, say here, and there's only a few over here. It only looks at these two and finds the middle of that. Midrange is really easy to compute, okay? We don't use it a whole lot because it doesn't give us a whole lot of information, but it is easy to compute. It really doesn't use all our data values though, so that's a pretty important reason why we don't use it. And sometimes the midrange is used incorrectly for the median, even though they're not the same thing. So make sure you understand the difference between midrange and median. If this was our example, again, back to the Verizon data speeds, and we got 5 of them. The biggest one is 55.6. The smallest one is 14.1. So if we find the average of those two, add them together, divide by 2, 34.85 would be our midrange. When it comes to rounding, one thing we got to understand is that every time we round, we create error in our answer. What we want to try and do is try and compute a final answer for any calculation with as little or no rounding as possible. When it comes to rounding at the very end of your calculation, what you want to do is use our typical round-off rule, which is to carry one more decimal place than is present in your original set of data values. So if all your data values had one decimal place in them, then the way you would calculate the mean or the median or the midrange would be to have, say, 2 decimal places in your final answer. Mode, we never really have to round because you're just looking at the data values themselves and using those as your mode, so there's no need to talk about rounding the mode. You would rarely ever, if never, round the mode. But for mean, median, mid-range, and really for almost all our calculations, this is our general rule. Carry one more decimal place than is present in the original data set. Again, try not to round until you get to the end of the calculation. If you were to round in the middle of a calculation to use to the next step, I always say the best thing to do is you're probably not going to be able to carry 10 decimal places and with any convenience. So if you know in the end, we're going to have one more than our original set of data values, which will tell you how many you know you're going to need in the end, carry two more than you know you're going to need in the end. And that should suffice pretty well in terms of reducing the error you would get in your answer to as little as possible. All right. So now that we've talked about mean, median, mode, and mid-range, and in the previous lesson we talked about frequency distributions, what we're going to do is now try and combine those two topics. So what we want to do is find the mean from a frequency distribution. Not a mean from a set of data values, but a mean from a frequency distribution. So you're looking at this formula, okay? One thing you got to understand is that this will not necessarily give you the exact mean, because in a frequency distribution, we will not know the exact set of data values we have. We will know where those data values fall, but we will not know what they exactly were. So this is going to be more of an approximation than it will be the exact mean. However, it tends to work out to be a fairly decent approximation. So what we're going to do is we're going to use our general idea of how we calculate the mean to do this. So first thing we want to do is we want to look at the class midpoint, and we're going to use that as a representative of the class. And we're going to multiply the first frequency of the first class by the midpoint of the first class, and continue that on, which will then have to add all those up and then divide by the total number of frequencies. I'll explain this in an example to give you better insight as to what's going on here.
Okay, so here is our frequency table we looked at back in chapter 2 in the lesson from last week. We have our different classes. Here we have the first class 75 to 124, and there are 11 data values that fell there. 125 to 174, 24 data values there. 175 to 224, 10 data values there, etc. for each class. If we add all our frequencies up, which is that symbol right there, it tells us to add the frequencies, add F, we get 50. So we know that there were 50 data values total, okay, just by adding our frequencies. Now, if we only have this chart here, and we don't have the data values sitting in front of us, but we wanted to calculate the mean, we can do that using this chart. But again, remember, this is just going to be an estimate, because again, we don't have the data values themselves to add up, but we do know that there were 50 of them just by staring at this chart. And so what we're going to do is we're going to find a way to get as close as possible to adding all our data values together. So what do we know? Again, we know that there are 11 data values that sit between 75 and 124. We don't know exactly which data values they are, but we do know that there are 11 of them in that range. So what we're going to do is we're going to find the class midpoint. And remember how we would find the class midpoint. We would do that by taking the upper and lower limits of a particular class, so in this case 75 and 124, adding them together and divide by 2. And that would give us 99.5. So what we're going to do is we're going to say that right there best represents the first class with a single value. If we're going to pick a single value to represent the first class, that does it. And so we don't know what 11 values we have, but we know that there are 11 of them in this range. So what we're going to do is say there are 11 data values that are exactly that right there, the midpoint. So there are 11 99.5s in our data set. Is that correct? No, but that is the best representation of the first class as a single value. So therefore, we're going to use that. And so if there are 11 99.5s, we would have to add all those up. Well, adding 99.5 to itself 11 times is the same thing as multiplying 11 times 99.5, and we get this value right here. So if we take the frequency of the class times the x, which should really be the midpoint, and I'll use MP there instead of x, I think that might better represent it. If we multiply the frequency times the midpoint, that would give us this number right here. And we'll do it again for the second class. There are 24 data values that fit into this class. We don't know which ones they are. Are they 126? Are they 127? Are they 170? But there are 24 in this range. So if we find the midpoint of that class and say that's going to represent the class, and we're going to say that there are 24 of those, we should multiply those two numbers together, and that's going to give us this. Again, that would basically be saying adding 149.5 plus 149.5 plus 149.5 over and over again 24 times. And we'll do that for every single class, okay? In which case, now we have to add all those up, because this is just adding up. This number right here just represents adding up the first class's data values. And this represents adding up the second class's data values. And this is the third class's data values. And we still have to add all those data values together. So we add all those numbers up, and we would get this number right here, which is equivalent to adding all our data values total from our data set. That's what's going to be the best representation of it. So we're going to add the frequency times the midpoint. In this x, we're going to use midpoint here. But to find the mean, you don't just add all your data values together. What you have to do is divide by the total number. So if we say this is how many total we would have had, because there are 50 in our frequency, we should divide that number by 50, and that should give us an estimate for the mean. And so if we take that number, 8,025, and divide by 50, we could say that the mean is 160.5. But again, remember, this is an approximation. This was not going to be perfect. The best way to find the mean is to actually know your data values. We won't know our data values in this case. And if we just have the frequency table in front of us, we still want to figure out what the mean is fairly close to. This is the best way to do it. It's not ideal, but it is usually close to what the actual mean is. So again, we're going to use the class midpoints as a data value from that class rather than knowing the data value itself. So that's it for section 3.1. Now we need to move on to this concept of measuring variation. So you need to learn what variation is and then how to calculate it. And we're going to leave 3.3 off for another time. Okay? So variation is probably one of the most important topics in statistics. It's definitely the most important topic in a first semester statistics class. A couple of things we're going to look at as it comes to variation. We're going to talk about range, standard deviation, and variance. The one we're going to focus most on would be standard deviation. We don't really discuss variance a whole lot in a first semester statistics course. It's typically you study that a lot more in your second semester statistics course. But we'll talk about it. What these do are they help us understand what's going on with our data set more so than the mean does. The mean gives you a little bit of insight. The variation gives you a lot of insight. Before we start calculating, we're going to talk about rounding, okay? So when it comes to rounding rules for variation, we're going to basically use the same rounding rule we had for center, is that we want to carry one more decimal place than at present in our original data set. Again, we want to try to avoid rounding as much as possible in the middle of a calculation. That's going to be even more important in the standard deviation calculation because it's going to be quite a lengthy calculation. So the less rounding we do, the better. Let's start with range because it's the simplest. The range of a set of data values is the difference between the highest and the lowest value. You just subtract the biggest value and the smallest value, and that'll tell you the range. And what that does is it tells you the span of your data values. The example I give a lot of times is grading. if I gave a test to 30 students and I calculated the average grade, the mean grade, and I got a 77 as my mean grade, that would be great. It's a C plus. Is it as good as I would like? No, but it's typical. 77, C plus is your middle grade. And then I would calculate the range. And if the highest data value, the highest grade was 100, and that's great, but the lowest grade was a 7, then my range would be 93 points between the highest grade and the lowest grade. And that's a pretty big span of grades. And as far as grades go, you don't want the span to be that big, okay? As a teacher, I would like the span to be fairly small. But again, the range gives you an idea of how far your data values span from the greatest to the smallest. So it gives you an idea of our variation, how our data values vary. Important property of range is that range only uses the extreme values, so it is not resistant. The range is very easy to calculate, so that's why we use it as one of our first measures of variation. It doesn't take into account all your data values because, again, it only uses the highest and the lowest data value possible, but it is fairly simple to calculate. So if we go back to our data speed question and we have our 5 data speeds, if we were to calculate the range would span, in this case, 41 megabits per second between the highest and the lowest data value. So that's the span across our data set. So that span here is 41.5 is the span. We could find where the middle is by finding, say, the mean. We know the lowest data value is here, 14.1. The biggest data value is here, 55.6. Okay. The mean we found to be something like 30 point something. And I think it was like 30.6. So there's the mean or the middle. And we know the span total of it, the range of those data values. The big one is the standard deviation. We're going to talk about it for the sample and the population, so I'll have separate symbols. So let's look at the definition first. The standard deviation of a set of sample values denoted by S is a measure of how much data values deviate away from the mean. So what is that saying? What it's saying is it's telling you how your data values relate to the mean in terms of how do they vary from the mean. I'll go back to my test question. I look at tests, all right? I know my highest grade was 100. I know my lowest grade was a 7. The mean or the average was a 77. Okay, there's your mean. That's the X bar, right? The mean from my sample, let's say. Okay. And now I want to say is, okay, that's all that information is nice to know, but I want to know a little bit more. So how do my data values relate to this mean? If I start plotting where all my test grades are, okay? So I have a test grade, let's say a 78, another test grade that's a 79, a test grade that's like a 90, another one down here that's maybe about a 50, and I start looking at them and I keep plotting them out here, and I keep looking at, okay, all my test grades, I start stacking them up if I get repetition of test grades, and I start doing this, and I start to notice that all my test grades are pretty much clumped right around the mean, okay? Then that's telling me that my data values, my grades for my tests, are not varying very far from the mean, from the average. And so most of the class was all about the same place. Okay? Their knowledge and their testing of that knowledge was relatively the same, right? There wasn't a whole lot of variation from that mean value. As opposed to if I gave you this picture where I have a couple of test grades down here, and a couple over here, and a couple over here, and they spread out much further away from that middle value, then there's a lot more variation away from that mean than in the first scenario. And the standard deviation essentially will calculate that. it will tell you, do your data values clump up right around the mean? Are they very close? Is there very little variation away from the mean? Or is there a large amount of variation away from the mean? So we have two symbols here. The sample standard deviation, we use lowercase s. We use this symbol here for the population standard deviation. Again, we're going to compare them. So we have the mean and of the sample and the population. We have the standard deviation of the sample and the population. You're going to see us look at either of them. What they represent is the same thing. How your data values deviate from the mean. It's just whether you're talking about a mean of a sample or a mean of a population. The formula we use for the standard deviation of the sample is this formula right here. There is another formula here, which is often called the shortcut formula. I don't find it to be a shortcut if you are using basic hand calculation to do this. This is a shortcut for calculators and software programs to calculate the standard deviation. They have an easier time of using that formula. But us humans doing it by hand, this tends to be the best way for a student who's first learning standard deviation to calculate it. So we'll focus on that one. Notice there's a couple of things in this formula. We know this symbol tells us we're going to add a bunch of things together. X represents a particular data value. X bar represents the mean from the sample. And lowercase n represents the number of data values in a sample. And obviously, you know what a square is and a square root is, etc. So it's a fairly complicated formula in that it's way more intensive than anything we've done so far this semester. And most likely, this will probably be the most intense formula you have to calculate over the course of the entire semester. But we find easy ways to do it by organizing our work. And so I'll show you how to do that to ensure that you get the right value for your standard deviation when you calculate. So before we look at calculating the standard deviation, let's just go over a couple of properties real quick. Again, what the standard deviation is. It's the measure of how much your data values deviate or vary from the mean. The value of the standard deviation is never going to be negative. One, because of how we compute it. Final step is to take a square root. But also just what it represents. If you got a 0 as your standard deviation, it basically tells you that your data values don't vary at all from the mean, that all your data values and the mean are exactly the same. If you have a very large standard deviation, that means that your data values vary very far away from the mean. And a smaller standard deviation would mean that most of your data values are clumped up and very close to where the mean is. But you will never get a negative standard deviation. The standard deviation can increase pretty dramatically when it comes to outliers, so standard deviation is not resistant. The standard deviation are in the same units as your original data sets. So if your original data set's in minutes or feet or pounds, your standard deviation is going to be in minutes, feet, or pound. Same thing with your mean and all the measures of center, really. The units of measurement from the data and from the mean and from the standard deviation are all going to be the same. And finally, the standard deviation is what we call a biased estimator of the population standard deviation. Okay, the sample standard deviation is a biased estimator from the population standard deviation, which basically tells us that the sample standard deviation S do not center around the value of the population standard deviation. Okay, they aren't necessarily going to be in the same location. So if we go to calculate a standard deviation, again, we're going to look at it in a fairly systematic approach. The more values you have in your sample, the harder it is going to be to calculate the standard deviation. So having a systematic approach will be helpful. So we go back to the Verizon data speed question. We have these 5 data speeds that we've looked at already. We want to calculate the standard deviation. A couple things we're going to need. We're going to need to know what the mean is. We've already calculated, in this case, 30.7. The formula looks like this. Okay, remember. So another piece that we're going to need is the sum of x minus x bar squared. And then in this case, that's going to come out to be 1083. And I'll show you where to get that from. And another thing we're going to need is n minus 1. Since there are 5 data values, n minus 1 would now be 4 because n is 5, the number of data values we have here. And so once we have all these values, we would take the sum of x minus x bar and n minus 1. We would divide those here. That's what's inside the square root. We would take the square root of that number, which would be the square root of 270, and we would get 16.45. And that sounds a lot easier than it really is, because the tricky part is getting this number right here. So if we have a systematic way of doing that, it makes it easier. So here's what we're going to do. We're going to create a table. And in this table, I'm going to look at my 5 data values here, okay? And I'm going to list them in the first column. And however many data values you have, you could list them in the first column. We would find the mean. So add them all up, divide by 5, we get 30.7. So then the next thing we want to do is we want to calculate x minus x bar. That's going to be part of the formula that we need. Remember, here's the formula we're working with. And so x minus x bar means take a data value and subtract the mean from it. So here's a data value. Here's the mean. So if I did 38.5 minus 30.7, I would get 7.8. Okay, that's x minus x bar gives me this. And then I'm going to do it for 55.6 minus the mean, and I get 24.9. 22.4 minus the mean, I get negative 8.3, etc. Okay. Now to make this more efficient, look at the next column. The next column is x minus x bar squared. So if this is x minus x bar, and this one's x minus x bar squared, to get from here to here, I take this number, 7.8, I square it, and I get this number right here, 60.84. Well, to make this go a little bit faster, rather than calculate this whole column first, and then calculate this column, what we're going to do is we're going to take this data value, we're going to subtract the mean from it, we're going to get this data value, and then while it's sitting in my calculator, I'm going to square it and get this number. And then I'm going to do that again. I'm going to take this data value, subtract the mean, get this answer. While it's sitting in my calculator, square it, I get this answer. And I'm going to keep doing that. Once I get this column here, I have x minus x bar squared for each one of our corresponding data values. I then have to add all the x minus x bar squareds, and that's where this 1083.06 would come into play. Once I have that 1083.06, I would then have to divide that. That would be this piece right here. I would then have to divide that by n minus 1, which in this case would be 4, and we get 270. Then once I do that, I take the square root of all that, and I get the 16.45. This number right here, which is the number before we hit the square root key, okay, to get the final answer, this number right here is what we call the variance, and we'll talk about that in a little bit. But that's called the variance. This number right here is your standard deviation. So if you create this chart, I think it helps organize your data a lot better. If you want, you could throw this into an Excel spreadsheet, and you could just come up with formulas to calculate this, where you just input these x's, and it's going to give you each one of these values all the way through. It depends on your skill level for putting formulas into an Excel spreadsheet, or you could just do it step by step like this. So it's pretty easy, but it definitely helps organize your work when you use this table format, as opposed to trying to do all of this calculation randomly. The range rule of thumb that we're going to use here is a way of understanding the standard deviation and what it tells us. Okay, and what the range rule of thumb says is that most of your data values, a pretty large majority, around 95%, should lie with what we call 2 standard deviations. Now, 2 standard deviations is 2 times the standard deviation. Okay? 2 times the standard deviation is 2 standard deviations away. So the idea is this. We have a mean of 30.7. And we have a standard deviation of, we just calculated 16.45. Okay? One standard deviation would be 16.45. And I could go one standard deviation away from the mean, and that could be above the mean or below the mean. So I could add it or subtract it from the mean. And then I could go another standard deviation away from the mean. So another 16.45 away from the mean. This is distance right here, and here is what we call a 2 standard deviation distance away from the mean. Most of our data values should sit in this box right here. 95% of our data values generally should fit in this box, okay? And we'll clear that up a little bit more, but the range rule of thumb basically says that this is where a majority of our data values should fall, in this 2 standard deviation window around the mean. All right, so let's now talk a little bit more about the standard deviation and what it tells us. So it tells us how our data values vary from the mean. So let's go back to this data speeds question. We found out that the average data speed was 30.7. So if you're in the airport, you have Verizon, your average speed you're going to get on your cell phone is 30.7 megabits per second. And that's great to know, like I said before, but what we want is a little bit more information. So the next thing is the standard deviation calculation. How do the data values vary away from that mean? And we just found out that our data values are varying away from the mean at a rate of 16.45 megabits per second for a standard deviation. It's a pretty big variation considering that you could go in either direction. So if I go in either direction away from the mean, just one standard deviation away from the mean, okay, and I'm varying at that rate away from the mean, I could be all the way up at like 46 megabits per second, or all the way down here at what, like 14 megabits per second. Okay, roughly, I'm estimating it here. Well, if I'm on my cell phone and you're telling me as a customer that you're going to give me an average of 30.7 megabits per second, but the variation is this wide of a variation just in terms of one standard deviation, that's not good. Yeah, if I'm up here, that's great because I'm getting a faster speed. What if I'm down here, okay, 14 megabits per second? What if I'm down this end and my internet is lagging and I can't really get what I want to happen on my cell phone? Well, that's a problem. I would think that a cell phone carrier would like to have a decent average speed and very little variation away from the mean. They would like this number to be very small. Okay? Comparatively, this number compared to where the mean is, that's a pretty big distance away from the mean, just in one standard deviation, let alone 2 standard deviations, and where most of your data value would fall. You would go below 0 on the lower end if you went 2 standard deviations away from the mean. Well, lower, you can't go lower than 0, and if you're at 0, it means you don't have any internet at all. So having that range on the bottom end is not good. On the top end, great, right? You're going faster than the average. But there's no saying that you're going to be in the top end range or the bottom range. So that's what the standard deviation is telling us. How do our data values vary away from the mean, and how much do they vary away from the mean? And depending on the situation, you may want that to be a smaller or a bigger amount of variation. I think for this data speeds question, I would want the variation to be fairly small. We went back to my test questions one, and I had an average of 77 on the test. I would like the variation to be small. I don't want my students to have a wide range of knowledge when they come out of a test. I would like most of my students to all have roughly the same amount of knowledge that was tested on the test and that they understood. So having a small standard deviation would be good in that scenario. Look closer at this range rule of thumb. We talk about significantly high and low values. We've talked about extreme values, outliers. Well, the range rule of thumb is this window of 2 standard deviations, okay? So you take the mean and you subtract 2 times the standard deviation to get this end. You take the mean and you add 2 times the standard deviation to get you this end, and this is where most of our values should fall. This is that window I was talking about. Values in here are not really that significant. That's just where most things should be. But anything outside that range, so anything on the lower end or the higher end, would be considered fairly significantly high or low. Those would be where your outliers would fall. So, we look at the middle range, but we also look at the top and the bottom end of what would be a significantly high or low value. The way we could do this fairly quickly, and again, the standard deviation is a calculation that's going to take you some time, and you're going to need to practice that quite a bit. Practice filling out the table, practice getting the calculations that we were getting. I think the more you do it, the better you get at it. But if we wanted to try and do this fairly quickly and get a real quick estimate of what the standard deviation is, one way we do that is by estimating the standard deviation by just taking the range and dividing by 4. It is not a very good estimate. It is a very rough estimate. But if we're trying to get just a quick look at what's happening with our data, say we're in the middle of collecting it, and we want to see how is our data starting to shape up. Maybe we need to make some changes into how we collect it. And we want to look at the mean and the standard deviation real fast. The mean doesn't take long to find. Standard deviation, if we want to do a quick estimate of it, we could do that range divided by 4. The population standard deviation, again, the symbol is this symbol right here. The formula is pretty much the same formula. We use population symbols instead of sample symbols, but the big difference is right here in that the denominator here, instead of being n minus 1, it's just n, in this case capital N, because population size is capital N. Now the reason for that is because of the difference between lowercase n and capital N. Lowercase n is usually a relatively small number, and if you subtract 1 from that and use that in your division, that tends to make a bigger difference in the overall value you would get here. Whereas if capital N was a very, very large number typically, and you subtract 1 off of it and use it in your division, it usually doesn't make a very big difference. So to simplify the formula, we tend to just use capital N instead of n minus 1 when we're doing populations, because it doesn't really make much of a difference. And if you think about it, if I have a population of 1 billion, say, in my population size, and instead of dividing by 1 billion, I divide by 1 billion minus 1, it's really not going to make much of a difference. Whereas if my sample size is only 5, and I divide by 5 or I divide by 4, which would be n minus 1, that would make a significant difference when you do division. Okay, so that's the reason. So just when you look at the standard deviation of a population and you're using this formula, everything would work out the same. You could create your table the same way. You would have your data values listed from your population. You would take your data value minus the mean, just the mean of the population instead of mean of the sample. Then the next column would be your data value minus the mean squared. Okay, that would be the next column. You would then, after you have this column, you would take all these values and you would add them up. And that's this part here. You would divide by n and then take the square root. So same steps, except for that very last one of n instead of n minus 1. Let's talk about the variance real quick. We're not going to use it a whole lot this semester, but the variance is the set of values of a set of values is a measure of variation equal to the square of the standard deviation. So it's a standard deviation squared. So if your standard deviation is the square root of the sum of x minus x bar squared over n minus 1, and you were to square that, okay, well, the square would get rid of the square root, and therefore the thing inside the square root is what your variance would be. Symbol for sample variance is the standard deviation symbol squared, and a population variance is the population standard deviation symbol squared. But it's just the number you would get before you hit the square root key and when you're calculating the standard deviation. So Technically, you can easily find the variance while you're calculating the standard deviation. We're just not going to study the variance very much this semester. So again, here's your symbols: sample standard deviation, sample variance, population standard deviation, population variance. One last thing we need to talk about is more about where your data values will start to fall in your data set as they relate to the mean and now using the standard deviation. So there's two ways we're going to do this. One is the empirical rule. The empirical rule basically talks about bell-shaped data. We talked about distributions last week. We talked about a bell distribution and what a bell distribution looks like. It has this basic shape to it when we're going to draw it. And so the empirical rule tells us where our data will fall with relation to the mean and the standard deviation. So what it says is there's three main numbers here. 68%, okay, of all our data values will fall within one standard deviation of the mean. I'll show you a diagram of all this in a second. 95% of all our data values will fall within two standard deviations of mean. That's why I said most of our data values should be in that two standard deviation block. And 99.7% of all data values will then be in three standard deviations away from mean. So almost all your data value sits there. Here's your basic picture that shows you this. So when we look at a bell distribution, the mean always falls right in the middle of a bell distribution. That's an important key. Okay? When you talk about measure of center with a bell distribution, the mean falls right in the middle. And then if we were to go one standard deviation away from that, okay, so take S and add it to the mean, take S and subtract it from the mean, and look at this block right in here. A good chunk of our data value should fall into here. And this says that 68% of our data value should be in that block right there. 68% of all data in a bell distribution should fall within that space. If we were to go two standard deviations away, so two standard deviations on the top end or the bottom end, that block should have 95% of our data in here. So 95% of all our data should fit in here. And then the final block, three standard deviations away, 97% of your data. So almost all your data should fit into that space there. Notice inside here there are these smaller numbers. One thing about a bell distribution is it's called a symmetric distribution in that the mean cuts it directly in half. So this piece and this piece should be equal pieces. So if it's 68% total, 34% and 34%. Now notice you have 34.13 and 34.13, and this only says 68% because there's a lot of rounding going on here. These numbers inside here are a little more specific than these general numbers up here. This whole picture will come back in a big way in a couple weeks when we start talking more about the percentage of data that fits into particular locations in a bell distribution based off of the mean and the standard deviation. But this is what the empirical rule says. So if we had an example like this and we said, okay, we're looking at IQ scores. And in IQ scores have a bell-shaped distribution if we were to plot them out. The mean IQ score is 100 and the standard deviation is 15. So what percentage of people would score between a 70 and 130? Well, if we look at this here, we draw our bell distribution. We know the mean falls right here in the middle, and it's 100. 70 would be over here. 130 would be over here. We have to figure out how far is that in terms of the standard deviation of 15. Well, we know this distance is 30, which would be 2 times 15. And this distance is 30, which would be 2 times 15. So these are 2 standard deviations away from the mean. And by the empirical rule, we should know that 95% of all our data should fit in there. So that tells us that 95% of all IQ scores should be between 70 and 130. And so that's what we just did. We're recognizing that these two values are 2 standard deviations away from the mean. 2 times 15 would give me 30. And so then, based off the empirical rule, 95% of all IQ scores should be in there. But this only works for a bell-shaped distribution. What if we have one of our other distributions that we've discussed? Well, then we have another rule. This other rule is called the Chebyshev's theorem. Chebyshev's theorem says you should be able to look at a portion of your data set lying within a certain amount of standard deviations away from the mean. And it says at least 1 minus 1 over k squared. Well, the only ones we really look at is 2 and 3 standard deviations. Okay, k is essentially the number of standard deviations. So the important part of all this is really sitting right here. Okay, this is what you need to get out of Chebyshev's theorem. And it says at least 75% of all your data values will be within 2 standard deviations, and at least 89% of all your data values will be within 3 standard deviations mean. Notice none of this says what distribution you need to talk to, and that's the key part about Chebyshev's theorem, is that there is no specific distribution here. So this works whether you have a Bell distribution, whether you have a skewed distribution towards one end or the other, whether you have a uniform distribution, or whether you just have some random distribution, right? You could still determine how much of your data should be within 2 standard deviations or 3 standard deviations using Chebyshev's theorem. If you know the distribution, let's say you know it's a bell-shaped distribution, we would do empirical rule instead, but this is a more wide-reaching theorem. So again, at least 75% and at least 89% are within 2 and 3 standard deviations. So here, let's say we were looking at IQ scores. Let's say we have a mean of 100 and a standard deviation of 15, but we don't know what the distribution is. So we have a mean of 100 here. We have no idea what the distribution is. It could be anything. We know we have a standard deviation of 15, so let's go with, say, 70 and 130 again. Again, we know that this is 2 standard deviations and this is 2 standard deviations. 2 times 15, 2 times 15, so 30 and 30 in either case. How much information, how much of our data should fit into this block? Well, because we don't know the distribution, the best we can say is at least 75%. Okay? At least, let's make it something you can see, at least 75%. So what that means is 75% or more. So the at least is pretty important. It means 75% or more of our data should be in there. We can't give it a definite number because we don't know the distribution. We don't know as much information as we do in, say, the empirical rule, because this has to work for a skewed distribution, a uniform distribution, a random distribution. So we can't give a definite number, but we can say 75% or more of our data should fit into that group, okay? And if we went even further, say 3 standard deviations away, we'll see that as well, right? So if we're 2 standard deviations away, at least, oh, I messed that up. At least 75% of your data should be in there, and 3 standard deviations away, at least 89% of your data should be in there. So 3 times 15 away from 100, right? So that would be 45 this way, which take me to 55, and 145 the other way. So at least 89% of all your IQ scores should be in there.